Sorry for the short delay. There was some problem with the PDF. My name is Roland. Compared to the other speakers that we had so far, so all of it was about forecasting. This will not have to do anything with forecasting itself. There's a bit of a mental shift. Now, this is about game theory. I'm not going to do forecasting. I'm going to do incentives for forecasting specifically. My name is Roland. Used to work at CB and in Delft. This work has been in cooperation with Hannah Boudre and New York Smith, WI and Delft, respectively. That's the Netherlands, Amsterdam, and Delft. And yeah, let's get right into it. So I'm first going to give you a bit of an outline of what's happened. I'm going to give you a motivation. I'm going to give you a research question, which also outlines the specific setting that we are considering. And then there's going to be a concept. And that's the part where I want you to really pay attention. That's the best prediction incentivizing concept. Then I'm going to give you a solution for this. And then we're going to look at real-world applications and how what the specific challenges is in applying that. There's going to be the word tunable solutions. That's going to be important. And arbitrage potential, which is basically just outsourcing your problem to other people, which I find is a nice thing. Motivation. It's actually pretty straightforward. There is an increase in fluctuating renewable energies because CO2 is bad and global warming is bad. That then comes with a need for flexibility. So once we have fluctuating renewable energies in the system and flexibility in the system, we would want to provision the flexibility optimally so that we can, use it in the moments that we actually need it. And for that, we want accurate predictions. So we want accurate models of our fluctuations in order to do better flexibility deployment. And that's the question that we're going to do. But more specifically, and that's where the setting a research question comes now in. So we're looking at a wind farm, for an example. Could be anything else. And on the other side of our equation of our peer-to-peer market, there's a flexibility provider. And so there's a wind farm that fluctuates and a flexibility provider that provides balancing for that. And they come to an agreement. We call that agreement a contract, feeder one. And that agreement outlines very simply that the flexibility provider will now take over the balancing responsibility of the wind farm. It will now react to any of those fluctuations, and the wind farm, on the other hand, just has to pay the flexibility provider some upfront cost and some payment for deviations, and that will result in a total cost. The very specific question or problem that arises from such a peer-to-peer market is those two entities are not owned by the same company. There's a wind farm and a flexibility provider, those are different companies, and the wind farm has knowledge about its prediction about the future, like its probability distribution of what tomorrow will look like, while the flexibility provider has the responsibility to react to that. So if those two are separate entities, what incentive does the wind farm have to share its prediction with the flexibility provider? Because it just outsourced this task via this contract. And that is exactly what we're looking at. The research question now becomes how to incentivize accurate predictions in non-cooperative settings. So how do we incentivize the sharing of predictions? And that's where best prediction incentivizing comes in. So where do contracts come from? That's the first question. We have a wind farm. It has some idea of reality. We're going to call that FD. And then there's a contract. But actually, there's not just contract. We're going to put in between a contract generating function, omega. So that omega takes in some prediction and outputs a corresponding contract that's going to change the upfront price that it pays for deviations based on that input. And the whole rest of the talk is going to be about this thing, of this generating function, and how to tune it and how to do it so that that's the right thing. So the property that we want to have, that's a lot of text, What it basically says is the generating function that we want to have should, for the correct prediction, output the lowest price contract. Because then the wind farm has an incentive to provide the correct prediction, because then it gets the cheapest contract. So now, since we are dealing with uncertainties and predictions instead of actual valuations, there's going to be a bit of complication here. So we have the wind farm, we have the generating function, and earlier I said, oh, it knows it has the correct model of reality. But that's actually not true. It has some F1 stuck in its head. That is some prediction of what it thinks that distribution will look like. And it will actually report that one. And then there's a true distribution, the actual randomness in the system. And we're going to represent that as this FT here. And there's some kind of difference between the mental model that we hold in our heads and the things that the randomness that actually exists in the real world. And there's words for this to describe this in the literature. It's the aleatoric uncertainty is the true randomness of the system, while the epistemic uncertainty is the difference between what you think about the world and what the true randomness of the world is. So now that the wind farm doesn't have access to the true distribution, but has just some mental model, we can't incentivize it to provide the true distribution because it doesn't know it. So we have to expand this best prediction incentivizing concept to a world where epistemic uncertainty exists, where this difference exists. That is, again, a lot of text. I'm sorry for that. But what it basically just boils down is, under epistemic uncertainty, we have to incentivize that if you provide a better prediction, you get a lower price. Not just correct prediction, lowest price, better prediction, lower price. And then that's all. So I'm not sure how many people here are familiar with game theory, but in game theory, that's this lovely concept of incentive compatibility. And that just says incentivizes true revelation. It incentivizes you to always provide the true valuation or true prediction or true whatever. And then our concept, that's prediction incentivizing, is moving towards the true prediction. And that's not quite the same. And the key difference between those two concepts is epistemic uncertainty. We're assuming that the agent doesn't have perfect knowledge and can therefore improve its prediction, and therefore we have to incentivize it to do that actually. So if there's no terms of epistemic uncertainty, those two concepts, they're just the same. Solutions, that's going to be very quick. So we have specific processing functions for those. We have this basic setup where for wind farm, it provides a parameter that describes a distribution, D, to our contract generating function, omega, out comes a contract. Or if we can assume uniform distributions or distributions of polynomial of degree k, we have solutions here for why this holds and what this looks like. Actually, you can just look into the paper. It's not very interesting. But what is interesting is the real world application of it. So we have this system here, and there's two problems with this in reality. And one is we assume a uniform distribution or polynomial distribution where there usually isn't one for our randomness. And the other one is wind farms might be good at producing electricity from wind. They might be very bad at predicting their future. So it might be that that they want to provide a better prediction. They just can't because that's not their expertise. So let's look at challenge 1, and for that, we just go fine-tune. We have on one side a model, a contract generating function of a polynomial, and on the other side, we're just going to assume some function. It's going to be, let's say the world is Gaussian. But what we actually have is a lot of functions. We have a family of functions, and what we can do is we can just pick one that looks like a Gaussian. So we go k star x such that it is Gaussian, and then we use that specific generating function for our process or wind farm gives us a parameter, out comes a contract. So now we have an approximate solution of reality, but that comes with two to much harder questions, which is, how good is this approximation still? So is this actually still does it still look like a Gaussian? And since our incentives were built for uniform or polynomial, does the incentive still hold? So for the approximation, we just plot Gaussians. So we have Gaussians, we have our model. It looks pretty much the same. It's pretty good. For the incentive, so this holds. For the incentive, it becomes a bit more complicated. And for that, I need to take a moment to explain something. So we have the wind farm. The wind farm provides a true, correct parameter of the world to our generating function while the world is Gaussian. Out comes a contract, and with that contract comes a cost. Then, but since there's a bit of a mismatch between this, the generating function, and the real function. And because of that, there's actually a more optimal value that it can provide that comes with a separate contract that has a lower cost. So there's, I don't know how I'm going to take a break here for a moment. No, this is serious because I had problems explaining this many times. Now, two things that I want you to pay attention here is there's a delta cost. This is how much the agent can gain the system, how much money it can get by reporting this instead of this. And the second part is the difference between this, between the true parameter and the optimal parameter, indicates how well do you have to know reality in order to gain the system. Because if you have only a vague notion of this, and the range actually includes this value, you're not going to gain anything. So those are the two things. Difference gives you the ability, and this gives you how much you can cheat. So very quickly, here's how much can we gain. This already indicates it. It's not a lot. So there's not much to gain by misreporting. And then we're looking at how easy is it. So that's again this value here. Was it this one? And we see that it's within less than 3%. So the agent would have to know reality pretty well in order to gain the system at all, and then not gain much. And that is actually also the conclusion. There's little to gain, and it's hard to misreport, which means that the incentive kind of still holds. So for the second challenge, the wind farm being bad at predicting, we have a wind farm. It provides a very bad prediction F1. It provides that with flexibility provider. Flexibility provider is not going to be very happy with that because it suddenly has to operate with a bad prediction and things happen that it didn't expect. So now let's say there's a middleman. And the middleman is just someone very smart who focuses on providing accurate predictions. Their job is just that. Their job is not doing anything else. They say, oh, I have a much better prediction. I have a prediction F2. So they're buying that contract. They're creating a new contract with their better prediction, and then they're going to sell that to a flexibility provider. So now there are two dimensions to this. There's exchange of power, and there's an exchange of money. With regards to power, it's very easy. Flexibility provider provides balancing to middleman. Middleman provides balancing to wind farm. The middleman doesn't do anything in this case. But money-wise, there is a difference because we tie the expected cost to the quality of your prediction. The wind farm is going to tie a high price to the middleman because it's bad. It was bad at predicting, while the middleman pays a low price to the flexibility provider for the same service because it has a good prediction. So as long as it improves the prediction, it can gain a profit. It's arbitrage in the purpose of providing more accurate predictions, which I think is legitimate arbitrage. That's useful arbitrage. Okay, conclusion. I would like to break it down to a single sentence, and that single sentence is epistemic uncertainty complicates incentives. Because the agent doesn't know itself perfectly, we cannot just use incentive compatibility. That's not enough. We have to incentivize them moving the whole chain moving towards the true distribution. But on the flip side, it also gives us an opportunity. because the agent doesn't know itself perfectly, something that only approximately incentivizes people would still incentivize people, because they would need to know themselves incredibly well in order to game the system. And okay, yeah, there's no last slide. Thanks. Right.